Good morning. Welcome to Krishna's class. We continue with our discussion on continuous functions on compact spaces. Let us briefly recall what we did last time and how compactness and continuity play together. Okay. So what is that we started with the following theorem. Suppose x, ex and y dy are metric spaces. X a compact metric space, F is a continuous map from X to Y is continuous, then F is bound. That means suppose you take any interval, example or a special case of this, suppose F from AB to continuous. Then F is bound. So that's a consequence of that. So the proof we have already discussed. Then, of course, what we proved was, suppose f is a continuous function from a compact metric space R, then it attains see by the previous result, see that f is from x to R continuous, x compact, therefore f is now suppose M is equal to supremum of and M equal to infimum of x belonging to x of fx, then which exists? Then there exists x1, x2 belonging to x such that f of x1 equal to now this is the conclusion. That means it not only exists, see, not only it's a bounded function, this is compact, then and you are talking about a map from a continuous map to R. Then it says there are points x1 and x2 such that f of x1 equal to the maximum value of f on the set capital X and x2 is the minimum value on the set. Okay, this is what we proved last time. Now we prove another result which says the following. Suppose I'll write down the statement of the theorem later, but let us understand the problem. X is compact. X is a compact space. And of course, we assume Fn is a map from continuous map from X to R. Therefore, this is continuous. So, continuous real valued functions on X we are taking. So, that forms a sequence. It's a sequence of continuous functions. Continuous real valued functions on X. Now we further assume Fn is a monotone space. Fn is a monotone sequence. And Fn converges to F where then what we assert is that or I will put it this way, Fn converges to F pointwise. Fn converges to F pointwise. Where F is continuous. Then sequence Fn converges uniformly So this is the conclusion that we make, namely what you have is a compact metric space. You are considering a sequence of continuous functions, continuous real valued functions on X with the further property that Fn is a monotone sequence and Fn converges to F pointwise. Pointwise. That means for each X, Fnx converges to Fx. For X belonging to X, where F is a continuous function. Then what we can say is that the convergence is not merely pointwise but much stronger, and say it's a uniform convergence. So this is the theorem. So let us make the statement of the theorem. This theorem is good. So this is the formal statement of that. Compact metric space let that means Fn's are all real valued functions, continuous for n belonging to. Then what you have, further assume that the sequence Fn is monotone. That means it is either monotonically increasing or decreasing. One of the two. That is, you have say Fnx for each x. The number sequence Fnx is decreasing, or is decreasing. This is the assumption that we have. That for each x belonging to x, the sequence fnx converges to fx, and the function f defined from x to r is continuous. Then the sequence fn uniformly so this is the uniform convergence is something that comes out of it. And the fact that X is a compact metric space plays a role in it. As we shall see, before we take up the proof of the theorem, let us look at this example. Where it doesn't happen. It's in the negative spirit that we are making this up. Okay. Consider zero, 1, 0 left out, with of course the metric inherited from now let us define the following function. So we define fnx to be equal to n over the interval 0 and 1 by n, and equal to one upon x okay. Now first of all you agree that this is a continuous function. What is a typical n? Suppose this is 1 by n. Then you are taking this function to n over here, and then you have n over here, and this is 1, and you are assuming from 1 by n to 1 the function, the graph of the function. This is it's not to the scale, it just conveys 1. So this is the function, this is your fn. 0. This is the graph of. So you immediately see that Fn zero one, the sequence is monotonically increasing. And what is your fx? Okay. To fx, I will write it what I have not said what fx is. Is defined as 1 by x for x belonging to 0. And this is monotonically increasing. Okay. But you know that the limiting function fx is continuous, but f is not uniformly zero one. So what goes wrong? How does it go against this theorem? Now what you observe is that the sequence, the space, the domain space, namely 0, 1, is not. So uniform continuity fails possibly if it doesn't say that for all sequences this happens. You can certainly construct a sequence where this happens, but there exists a sequence which is monotone and continuous functions, monotone continuous functions, and it converges to some f or the interval, but the convergence is not uniform. The reason is this: the domain space of Fn and F is not. So that's a example which highlights the significance of the compactness of the domain in the statement of this theorem. Now let us explore this proof of this. Proof is quite simple, but certainly worthwhile to look at. If you want to know how this compactness is made use of, assume the sequence Fn is increasing. We prove the theorem assuming that Fn is increasing. The same proof can be modified with the assumption that Fn is increasing. We can so we give the proof with the assumption that Fn is a monotonically increasing sequence. Now define F or Gn F minus G. Sorry. That's the definition of Gn. Decreases to zero for each monotonic. Okay, decreases to zero. So now what do? We choose to prove the uniform convergence. What you have to do for a given epsilon, you have to show that there exists an n which is dependent on epsilon but not dependent on x, such that whenever Fn minus f, that is a norm of Fn minus f, goes to 0, or Fnx minus fx modulus of that goes to 0, that means Fnx minus fx modulus of that is less than epsilon for all x and for all n greater than a particular n which does not depend on x. Okay, so let us explore. So this is what we want. N See what is happening to Gn. Gn goes to 0 at each point. Okay? Then for k belonging to n, so this is what we have. Decreases. Okay. Therefore, we define for each k belonging to n, define uk to be the set of all x belonging to x such that so what is that we are trying to prove? We are trying to prove that uk gnx converges to 0 uniformly on x. Okay? That's our claim. That is, which in turn means that Fn converges uniformly to F on X. Okay. So we choose these sets. Now what are these sets? So our UK is equal to GK inverse of minus infinity what does this mean? Let's take care. Try to understand this. What you have is you have a sequence of functions. Suppose we are taking the example 0 to 1. We are taking the compact set. So this is GK and we choose epsilon. Choose epsilon plus. Now, where the function is less than epsilon, see that this is where the function is less than epsilon. So this one. So this marked portion is where G is less than. So this is your. What do you know about GK plus 1? GK plus 1 is something that is still less than GK at every point. Of course, it is equal in some places, but certainly it is not. It is monotonically decreasing. So it is something like this. This is GK plus 1. Now what happens? Now you see that let us mark UK plus 1. What is UK plus 1? Mark UK. This is UK plus 1. So this portion, what you call it? First we shall write, tag it with the color. Okay. Now what can you say about? So this is your GK inverse of minus infinity to epsilon. And now you see that continuous UK is open because it's the inverse image of an open set. Further, easily observes that UK plus 1 or UK is contained in that is if x belongs to UK, then goes to 0, or rather monotonically decreases to 0. There exists a such that GKX less than x. And also, and what you have is the following GKX1 GKX, and that is less than, which implies 2K so this is a monotone sequence. Okay. Now you see that UK now look at this collection. Open intervals, in X, and we have X contained in So this UN provides X with a open cover. Now since K is compact, X is compact, there exists a finite subcollection of UN covering let us designate this subcollection by that means there are such elements of UNs which will give you a covering, or that is X is contained in that is coming out of compactness. Now choose, let N be maximum of K. We have also the monotonicity. Using the monotonicity, see that you have this equal to consequently for every n greater than or equal to n, x belonging to x, we have gnx less than or equal to gnx, which is less than x. That is gn converges, sequence gn converges uniformly zero to g identically equal to 0, or which implies the sequence fn converges uniformly to f on on okay, where we have used this f is continuous because we have defined Gn as Fn minus f. We call our definition Gn as f minus f. And we have used the continuity of Gn. And Fn is continuous, f is continuous, therefore f minus Fn is continuous. So we have made use of that. Okay, so that proves the theorem. So given epsilon positive, there exists an n such that Gnx converges to Gn for every x belonging to x and for every Fn converges to f for Fn minus less than epsilon for every x belonging to x and which depends only on epsilon, not on x. That is what we have proved. Okay. So which in turn means that Fn converges uniformly. So, okay. Now we have seen in the example that we have looked at that if this condition of compactness of x is dropped, then we are not likely to get uniform convergence. Now we will explore this further in some examples later. We make the following remarks. They are just problems related to this. Let continuous fx is greater than or equal to epsilon for every belonging to x. What does this say? See, the function f is, so we will just give the sort of explanation. Note that f is non-negative function. It's compact. Which is compact? Now you know that since f is continuous, and x compact, we use the previous theorem. What does the previous theorem say? F attains a maximum on x. So let us take the case of fx attaining the minimum. A point where then what you get? By the definition of the function, f of x naught is strictly greater than 0. Because f is since now you choose which is positive. Then what we have is that f of x is greater than so that gives the proof of this. Second point. This is very important. Continuous image of a compact matrix space is compact. So let us explore this. How will you do this? So let f be from x to y. X is compact and continuous, and f is continuous. Now we take f of x. Let v alpha alpha belonging to phi be an open cover for fx. What we want to prove is that for every open cover there is a finite subcover. So let this be an arbitrary open cover for fx. Now we want to show that there exists finitely many elements of this which will provide a covering for x. Okay. Now since f is continuous, what do we get? We get f inverse of E alpha is open. Next. Open inverse. Not only that, further x's contained in it's an open cover for E alpha. So that is this collection is an open cover show that if you take any x, then it is in one of these f inverse of yeah. That is quite easy to see because x gets mapped into fx. And you have a cover, you have pulled it back. Therefore, look at this. I mean, that's easy to see. Since x is compact, what do we have? X is contained in V alpha Q for some. Or there exists a K such that this is true. Now x belonging to x implies x belongs to f inverse of B alpha I for some I for some So what does this mean? This means that therefore V alpha 1, V alpha 2, etc. V alpha K is a finite subcover for that is the open cover subcover V alpha 1 that is f of x is open. So look at the argument. We started with an open cover, an arbitrary open cover for x. And then pull them back. So we got a open cover for x from it. So we started with an open cover for fx, and from there we got a open cover for x. Now we use the property that x is compact, therefore it has a finite subcover. And then pulled it back to the and then we pulled it back to the space y, and we get V alpha 1, V alpha 2, V alpha k, and then we prove that this forms a finite subcover for fx. So fx is compact. It's a very important result that continuous image of compact sets is compact. So more generally, suppose x and y are homeomorphic. This means it is 1 to 1, on to f is continuous, and f inverse is continuous. I'll explain it out. Then if x is compact, y is also so, or x and y are compact together. That is what it is. Okay. What does this mean? F is homeomorphic. Just spend a second on that. So we have the following conditions. So we have f from x to y. Their excess f from x to y such that 1 f is 1 to 1. 2 f is equal to, that means 1. So this together say it's a bijection. Now the third condition is f is continuous. Since x and y are metric spaces, clearly we are working on metric spaces. Okay. F is, so you can talk about continuous. F is continuous. And since f is both 1 to 1 and on to, f inverse is from y to x, x is, now assume continuous. So this is what you mean by continuity. So f is a bijection and f is also bicontinuous. And if such an f exists, then we say x is homeomorphic to it simply means that as metric spaces, they can be identified. One is simply a distortion of the, okay, that will be the geometry. A continuous distortion of, or what you call a bicontinuous distortion. Okay, so this is what you mean by homeomorphism. And the consequence of homeomorphism is that x and y are compact together. If x and y are homeomorphic to one another, then x and y are compact together. Okay. So this is why it is often called a topological property. In the sense that compactness is invariant under a homeomorphism. Of course, one can easily show that continuity of, even if F is a bijection, continuity of F need not imply the continuity of that you can explore. Okay. That's why you specifically say that the first two conditions assure that F inverse exists, but then you are assuming that is. That's why you say F is bijection. Okay. Now we prove another consequence of this, the interaction between continuity and compactness. So next here, any continuous function is an important section. From a compact space, to another metric space. Is uniformly compact space. Another metric space is uniform. So continuity is uniform. The domain is a compact metric space. Okay. Now let us look at some case where this may not, the uniform continuity may not be. Okay. Suppose you take this. Let F be from defined by one by x. This is a well-defined function. F is continuous. This is not compact. It's not compact. And F is not uniform. Now just recall the following result. That is the see which intervals are not compact on are or which subsets are non-compact. We call a subset compact if and only if it is and bounded. Now in this example we consider a bound is bounded but not closed and hence not compact. Now we take another situation. Now consider f from defined by x. So this is continuous. Zero infinity is closed, but not bounded, and hence not compact. Now observe that uniform. So the two situations of subintervals of R being non-compact has been explored. In both the cases, we have proved that there exists continuous functions which are not uniformly continuous. Okay, so we will come back to the theorem and then prove it. Okay. So continuous images of compact sets. Sorry, this yeah. So the theorem is, we'll restate it. White off any continuous function from a compact space another metal space. Is uniform values. So let us prove this. Let us see. So let f, so x and x is compact. Let then what we claim is this. So what do you have to prove? This is what you have to prove. Given epsilon positive, there exists positive such that dx of dy of this is what you have to prove. So let us work out a proof for this, where we use the compactness of x. So given epsilon positive, by the continuity of s, at any x belonging to x, there exists an Rx positive such that dx y Rx implies the important thing is that this Rx depends on epsilon as well as x, because we are talking about continuity at the x. Now what we do is, so you have So you are taking a point X. What you show is this. Now, what you have shown is that given an epsilon neighborhood of fx, that's the fx epsilon, there exists a p this is in y, this is in such that f of now this is the definition of country. Okay, that means this Rx neighborhood gets mapped into the epsilon neighborhood. Okay, so every point here goes inside this. You take a y here, then that y fy is in. Okay. Now we take the balls with the center at x and radius Rx by. Rx. Okay. So consider this collection now. Rx by 2 this is an open cover x because at each point x belonging to x you have such a neighborhood that you have chosen. Therefore, that is x is contained in this is obvious, nothing to prove. Since x is compact, it has a finite subset. Say Rxi by 2 for in other words, what we are saying is that there exist points, there exist and it is a finite subcover, it is a finite subcover of the open cover that we have considered. Okay. So let us, for convenience, let us write Ri equal to Rx. And now delta be defined as minimum of for I equal to, because these are finite positive numbers, it has a minimum and that minimum designate as delta. Now we choose let be such that dxi less than that. Then this implies I think I'm confusing the equations. Okay. Please stick to this one. Okay. Then what you have? See, there are only finitely many these collections. Therefore, you should have some, uh, you know, x. Then x belongs to by 2 for some I. Okay. Also, y belongs to b xi r. Because of this assumption that this is less than delta, and the delta is the minimum of Ri by 2 for I running from 1 to n. Therefore, see what you have is this. So this is your x. Okay. This is your xi, and x is I, right, larger. Okay. How is this? So in x you have some xi. You have got this is Ri by 2, and x is an element of this. X is an element. Okay. Now you have this is bxir. This is bxi. That is the difference. Okay. So x is some point. X is some point. Because dx xy is less than delta. And what about, so we are assuming dx xy is less than delta. Therefore, the condition that dx delta, and which is the minimum of Ri by 2, I running from 1 to n, implies the following. Y also belongs to it cannot be outside that. If it is outside that, then you see the distance between x and y. See, if x is here and y is here, then you see that if you compute the distance between x and y, it is going to be greater than Ri by 2. What does it mean? This is Ri by 2. Okay. So if greater than. Okay, so the condition that dxy less than delta means that this is x is in, if x is in b xi ri by 2, and then y has to be necessarily inside b xi ri, because outside that would mean that the distance between x and y is greater than delta. So that is the picture that you have. Okay. Now let us work on this. This is because this one, see, dy xi, let us give a formal for this. Xi is less than or equal to dy x d psi. Therefore, this is, of course, less than or equal to delta plus Ri by 2. So this is true. Why belongs to dx? Now we compute this. So what about this is less than e psi plus so all y distance in the metric space y and this of course this is less than epsilon, this is also less than epsilon. Rx is chosen such that I don't know whether I wrote epsilon by 2 in the beginning. If I have not, please correct it. And this is to be written as epsilon by 2. I'm not sure now because I have already erased it, and unless I go back, I cannot find it out. Okay. So otherwise, this is what you have. So given epsilon, for epsilon by 2, you take the corresponding Rx, and then the analysis works. So this would give you that F is uniformly continuous. Okay. Now I think I will wind up the talk at this stage and then go further with it in my next lecture, which may be this afternoon or tomorrow. Thank you very much.